Look out! I think Moto likes you. Here he comes.
In this video, I'd like to talk about distance versus displacement. Distance is the total distance traveled, whereas displacement is just how far something is from its starting position. So in this picture, displacement is the ball's position at A and the ball's position at B and the distance between those two places. But the actual distance the ball traveled is a much different story. It actually traveled way farther up here than you would imagine if you just considered its displacement. Now, let's imagine some particle that's moving at a velocity of 3t minus 5 meters per second. Let's imagine a particle with this velocity, 3t minus 5 meters per second. And let's look at a graph of what this would look like. If we graph this, it'd be 3t minus 5, so y-intercept down here at negative 5, and then it increases at a rate of 3. Okay. And let's say you wanted to find the distance and the displacement over the first 3 seconds for this particle. So we're going to find the distance the particle traveled and the displacement for this particle. Well, let's consider this. Since we have a velocity function, this is a rate. We want to find distance in meters, displacement in meters. We already know we're going to integrate this for the time that we care about. And we said we're going to care about the time from 0 to 3 seconds. So let's find how far it traveled total and then also its displacement over 3 seconds. Well, let's think about this visually before we apply any integrals. Let's say we have a velocity function, we want to find distance displacement, so we're going to find the area under the curve from 0 to 3. Well, for this first part, it's here, well, the area between the curve and the x-axis, and then from 0 and then to 3, maybe it's going to be something like this. So we can already start to see that distance and displacement are going to be a lot different, because displacement is just integrating from 0 to 3, this velocity function, and displacement does not care that this part or this area is negative and this part is positive. It's just going to put those two together and see how far this particle is from where it started. Maybe if the negative part is less than the positive part, this particle ends up a little bit to the right of where it started. Maybe if the negative part is larger than the positive part, this particle ends up a little bit to the left of where it started. However, that's not the whole story, because the distance is going to be something different. Let me write that down here to make a little more space. So the distance it traveled is going to be adding this area and this area. The distance doesn't care that this was negative, moving in the negative direction, and this was moving in the positive direction. The distance will be adding all those things together. So let's go ahead and see if we can actually calculate the displacement and the distance. To find the displacement over the first 3 seconds, all we need to do is integrate 3t minus 5 from 0 to 3. Now we can do this one of two ways. We can use the reverse power rule, or we can use our calculators to do this. In this case, because it's just 3t minus 5, I'll set it up by hand using the reverse power rule, and then I'll actually go ahead and calculate it using my calculator to save a little time here. So we know when we integrate this, we'll use the reverse power rule. That's 3t squared over 2 minus 5t. And we're going to evaluate that from 0 to 3, which means we'll plug in 3. And then we'll subtract what happens when we plug in 0, but we already know that's going to be 0. Okay, it looks like this one's a little bit easier to calculate than anticipated, so we can just finish this off. That's 3 squared times 3, 27 over 2, minus 15. That's 30 over 2. So it looks like we're going to get negative 3/2 as the displacement of this particle, which means that after this particle moves for 3 seconds, it's negative 3/2 meters to the left of where it began. Now let's calculate the distance the particle traveled. We know it ended up 3/2 of a meter to the left of where it began from integrating from over the first 3 seconds from integrating from 0 to 3. But we want to know how far it traveled on its path. And in order to do that, we need to add up the negative area and pretend that this is positive because it did travel this amount, even though this was in the negative direction, and we'll add it to the positive area. So we need two separate integrals to get the answer here. We need one that shows the negative area and one that shows the positive area. And we also need to know, most importantly, is where does it switch over from under the x-axis to above the x-axis. In order to find that, that's really a question of where is the x-intercept for this function. So we need to quickly calculate the x-intercept. That's 3t minus 5. Set it equal to 0 to solve for the x-intercept. 3t equals 5, and t equals 5/3. So this function will change from moving to the left to moving to the right at 5/3, which means we need two separate integrals. One from 0 to 5/3, and one from 5/3 to 3 seconds. And once again, I'm saying we're going to 3 seconds here. We're just looking at the first 3 seconds of this particle. Now, this would give you a negative area. This would give you a negative number, but we don't want a negative number. We want to know a total distance traveled. So what we can do is put a negative sign out front. If we negate this, it'll be a negative negative, and that will give us a positive value for this. We'll add it to this, and that'll give us our total distance traveled. Let's use a calculator to calculate the answer to this one. Let's go to math. We'll go down to our integral, but before we do that, we need to put a negative sign in because we know that first integral is going to give us a negative area. So like I showed before, if you put a negative sign in, it'll cause this to be positive. So we'll do negative integral 3x minus 5, comma, x is the variable of integration, comma, from 0 to 5/3. That's the distance it traveled over the first 5/3 seconds. Then we'll add that to our integral of the function 3x minus 5, with x being the variable of integration, from 5/3 to the end of the 3 seconds. And it says 6.833. We'll convert that to a fraction, and it's telling us that this particle traveled a total of 41/6 meters in its first 3 seconds.